So our next speaker is Luca Lingardo from NXP Semiconductors, and he's going to talk about implementation of an edge computer architecture based on a RISC-V core for RFID communication. Hi, Luca. Thank you so much.
Hi, good afternoon. So I'm Luca Lingardo. I work at NXP. Today, as already announced, I'm going to talk about the vision of NXP of bringing a RISC-V-based microarchitectures at the computing edge of an NFC device. So let's go a moment through the agenda. I will give first an introduction about myself, my business line, what we do in our team. Then I'm going to talk about near-field communication. We'll give a fast overview and what's the problem statement behind the current architectures of NFC, and how we plan on solving these issues, these limitations with the RISC-V-based solution. And at the end, I'm going to talk about our future ambition and how we plan on achieving our goals. So let's go to the next slide. So about myself, I'm a senior digital design engineer. I'm working at NXP Semiconductor in Austria. At the moment, I'm the technical coordinator of my team, and on top of that, I'm also coordinating one of the Tristan work items for new IP development that work with the extension of ISA. My business line focuses on the development of NFC solutions for the IoT market, mobile wallet, and secure transaction and access. My team is responsible for the development of the NFC digital modem, so basically the unit that packed the information before transmission and unpacked the information in reception. The activity I'm going to talk about today is sponsor-funded by the Tristan Consortium, and we are closely collaborating with many universities. At the moment, we have master thesis students and PhD students from the Polytechnic University of Turin and the Technical University of Graz. So about our side, we are based in Gradkorn, in the vicinity of Graz. Our site counts for 700 employees, more or less. And we have 5 product lines focusing on automotive, IoT, and security. So let's talk about NFC. So what is NFC? NFC is just an umbrella of radio frequency identification standards that operate at 13.56 megahertz. This set of protocols allow for close proximity communication between two devices, and NFC devices are currently deployed all over the world in billions of pieces for mobile payment, secure identification and access, wireless charging. But the use cases can vary even more. How does NFC work? So basically the communication happens between 2 main actors. We are talking about an initiator and a target. The initiator generates the RF field and starts the communication, and the target responds to this RF field by either modulating the carrier frequency. In this case, we talk about passive communication. We talk about active communication when the target responds to the initiator by generating its own field. I'm sorry, in the slide there is an error, a typo. I talk about the initiator. But okay. So let's go to the main mode of operation. We have 4 modes of operation in NFC devices. We have reader mode, where the NFC device works as a point of sale. Card emulation mode, the NFC device works as a credit card. Peer-to-peer is when 2 NFC devices talk between each other. Charging mode, when the NFC device charges another electronic device. So here I wanted to represent an high-level overview. It is intentional that it's not detailed, but I want to give an high-level overview of what's an NFC SoC today, more or less. So from right to left, we have the analog chain. We have an analog transmitter and analog receiver in general. This is connected to an antenna. After that, we go in the digital domain, where we have what I'm calling the NFC digital modem or NFC modem. Again, the unit that basically pack the information in transmission and unpack the information in reception. and the NFC modem is connected to the main CPU subsystem through an on-chip bus. What is the issue of this architecture? Or what is the problem we try to solve with our research? So with this architecture, the NFC device has to perform a considerable amount of analog and digital signal processing with custom logic. Why is it needed? Is it needed because you want to achieve high performance and robust communication over different operative conditions with different devices all over the world? And on top of that, we have seen before that the NFC standard is an umbrella of multiple standards, so you have to support different standards, so not just one standard. So what is the main issue? The main issue of implementing very complex signal processing operation with custom logic is that once you go in tape out, once you send the hardware out, you have limited functionality flexibility on silicon, so you cannot add a new feature, at least easily. And if a new standard is out and you want to support it, it's difficult, or in this case, quite impossible to support a new standard. Of course, DSP operations are difficult to support. Finding bugs is the norm, and mitigation action on if you find a bug on silicon are limited. And obviously, to tape out such a complex system, the pre-silicon engineering effort is quite high. I also want to add another drawback that I didn't list here, that is basically in current architectures, for every standard you have a sub-DSP unit that takes care of the standard, and of course this increase the area requirements of the chip. So how do we, what's our vision? What do we want to do? As I said at the beginning, we want to put a RISC-V core, so a microprocessing unit based on RISC-V at the computing edge of an NFC device, and the RISC-V core should take care of executing the real-time DSP operation. The advantage is that we have enhanced silicon flexibility. We can support more standard once the silicon is out. We can also support more features. The pre-silicon engineering cost will go down, will drop in our opinion. Of course, the disadvantage is that we can have higher clock rate to ensure real-time operations, but also higher resource usage like memory requirement, but also area requirements to implement the microprocessor unit. About related work, I've not found anything similar on the IEEE publications and other journals. So this gives even more value to this research that we are starting. But in general, the advantages of using a microcontrolling unit at the computing edge for wireless communication is a well-known solution that was proposed in other papers. So about the proposal architecture, so as I said, we are going to integrate the microprocessor subsystem at the computing edge, so we will have the analog front end will remain untouched. And in the NFC digital modem, we want to integrate the microprocessor subsystem based on the RISC-V core. Our target is that this microprocessor subsystem has to support DSP operation for the receiving chain, so I cut the transmitting chain. The microprocessor unit should be clocked with a clock that is 4 to 8 times higher than the main NFC digital modem. So as for NFC, the frequency is 13.56 megahertz. We are talking about 50 to 100 megahertz of clock requirement. And the main component of our high-level architecture are obviously the RISC-V core. Then we have a dedicated interface to route selected signal from the NFC digital modem to the microprocessor subsystem. We have a DMAC for fast transfer of data into the memory. We have an on-chip bus manager and subordinate connection, and of course interrupt controller and timer units. So let's talk about the current status of the activity. As I said before, this activity is performed under the Tristan project. We started more or less 1 year ago, and we are following 2 tracks. So the first track is kind of a proof of concept, allowed us to understand that we can achieve our goals. The second track is more long-term, more explorative, I would say also more challenging. So let's start with the first one. We have implemented a microprocessor unit based on an NXP proprietary RISC-V core. In this case, the architecture that we have selected is exactly the same that I presented in one slide before. That was our first high-level choice. The implementation status of this microprocessor unit is quite advanced. So we have done the implementation, we have done the integration at the moment. We are finishing the verification stage, and we hope to tape out soon. In this case, the microprocessor unit will be in charge of executing some auxiliary DSP operation in receiving rather than supporting for the exchange of information with another NFC device. The selected RISC-V core instantiates an FPU to improve DSP operation precision. The clock frequency that we are operating at the moment is 4 times higher than the NFC modem clock frequency, so we are talking about around 50 megahertz. And of course, we have tested this hardware solution with some firmware running on top of this RISC-V core, and our proof of concept is real-time monitoring of an RF field shape for low-power tag detection. So let's go to the second activity. As I said, it's more a long-term activity, so we plan of coming with some solid results at the end of 2025. And in this case, we are implementing a microprocessor unit for the same purpose, but based on an open hardware RISC-V core. We have selected the X extension of the open hardware RISC-V core families because it allows for, it has an ICE extension port, so allows for ICE extensions. The development status is in an early stage. Let's say we have run the first prototyping activity last year, so we got some results already, but they must be improved. In this case, our ambition is not to use this unit to run auxiliary DSP operation in reader in RX, but we want to substitute the DSP core of the NFC modem with this solution, so supporting all the NFC standards. At the moment, our target is to receive a tag response, so a target response of a type A 106 kilobaud rate message is one of the standards supported by the NFC modems, NFC forum, sorry. And at the moment, the results that we have obtained during our last year implementation activity is that we have implemented the coprocessor unit to enhance performance that we have put together with the RISC-V core. The coprocessor unit focuses on supporting MAC and SIM distractions, and we can, at the moment, correctly demodulate the type A 106 tag response. What's the problem? The problem is that we need a around 500 megahertz clock to support real-time operation. So this is unfeasible in the IoT market. So here I just want to give a high-level overview of the open hardware core plus the coprocessor. You can see the extension port. We'll just go fast. This is the coprocessor architecture, a high-level overview again, and this is the MAC architecture. So let's go to the future ambition. So the short-term ambition of this project is to, so again, our target is to demodulate a type A 106 tag response, but we want to improve the clock constraint, the area and memory requirements, and so on and so forth. I wanted to say that this is an hardware-software co-design activity, so we don't want to provide just an hardware solution, but a software solution and hardware-software are closely cooperating for this architecture. And the focus for the Tristan project is to integrate this solution in an existing NFC SoC. The long-term ambition is to support all the standards of the NFC forum, and also having the flexibility to adapt the architecture to new standards and new features on silicon. I'm done with the presentation. Thanks a lot.
So we have time for a quick question. There's one there.
Hi. You talk a couple of times about your clock, higher clock rate. So
Yes.
how is that affecting the use of this in, for example, some devices that are, battery operated and things like that? What about, power consumption? Because of course, most of the readers that are mostly, basically stationary or something like that. But in some cases, you have that other problem with. So are you expecting a higher power consumption as well?
Implementing the full architecture.
Exactly.
So let's say that's one of our drawbacks. But since the focus is to support the NFC forum in total. So NFC forum is a lot of standards. So a lot of standards means a lot of custom logic, cost a lot of static power consumption, for instance, and so on and so forth, and also area. So if we manage with our ambition to eliminate all the DSP part that support all the standards in reader mode, card mode, and so on and so forth for all the standard and all the rates, the overhead of consuming more probably dynamic power consumption will be covered by the advantages of having, sorry?
Balance out.
Yeah, balance, exactly. We cut all the DSP parts, so less leakage power, less area, and so overall we think that we will have even a smaller chip that consume less power as well. Yes.
Thank you again, Luca.
Thank you.